So in this video, we're going to discuss diffusion and effusion. And these are two concepts, especially diffusion, that are related to our sense of smell. So diffusion is the movement of gas particles. It could be any particles, but since this is a chapter on gases, we're going to be talking about diffusion of gases from an area of high concentration to low concentration. So this is why if somebody, opens up a bottle of some nice smelling liquid, or they open up their lunch or something at the end of the room, it might take a little while, but you will smell that, right? Those gas particles, that vapor that smells good from their lunch, is going from an area of high concentration from their container all the way to your nose at a lower concentration on the other side of the brain. Effusion is related to diffusion, but it is the movement of gas particles from high concentration to low concentration. Usually we think about this as a vacuum, for example, through a small hole. So you have a container with a gas in it and it's sealed, and you poke it through a small hole in it. That gas will escape that hole, and that is called effusion. And there's an expression that tells you the relative rates of effusion of those gases, and it's related to their molar mass. So in particular, the square root of their molar masses. So if you have some mixture of gas A and B, the gas that has the lower molar mass, or this gas A is in the denominator, that will move faster, right? And that's what we expect based upon the previous video where we talked about the average speed of gases. Gases move faster if they're lighter, if they have a lower molecular weight or molar mass. So here's just saying that again, and a little bit of the derivation of this equation. It comes from square root 3r t over m1. That was that average speed equation that we had in the last video. And now you're just doing the rates, relative rates. So you divide these two expressions together, the 3RTs cancel, and you end up with just square root of m2 over the square root of m1, or the whole thing square root. Mathematically, that's the same thing. So let's use this equation now in a practice problem. So the problem states that at constant temperature, dinitrogen tetroxide fuses 1.37 times slower than an unknown gas. What is the identity of the gas? So this dinitrogen tetroxide is a gas, and it is the slower effuser. So that means that what we're looking for is the faster effuser, which means that it should have a lower molecular weight than N2O4. And so all we have to do is we have the relative rates, and it tells us 1.37 times slower. So we plug that in to our rate comparison here. And then we plug in the molecular weight for dinitrogen tetroxide, right? 14 times 0.01 times 2 plus 16 times 4. So 28.02 plus 64 gets you 90.02 grams per mole. And then divide by the square root of x. We don't know the molecular weight of that other gas. That's our M1. But if we plug that in, we'll get an answer. If we solve for x here, we will get an answer of 48, which is 16 times 3. So that's the molecular weight of ozone. So indeed, we did get a smaller molecular weight. So you just have to be a little careful here how you plug this in. Are you going to want to call this M1 or M2? But we know it's going slower, and so the slower one is going to be on top, right? M2. Okay. Let's do a more difficult version of this problem with relative rates. This one just has a little twist to it, and so let's work through this. A gaseous base and a gaseous acid. We're given the identity of the acid. It's hydroiodic acid. are placed on opposite ends of a meter-long tube, okay, and allowed to fuse. A white precipitate of salt forms 0.267 meters away from the acid. What is the molar mass of the base? So let's draw out what this experiment really means. What it means is we have a tube, okay, and we kind of have a plug, maybe like a cotton plug or something, on each end of the tube, and there's a little hole poked in it, but that cotton plug contains the acid in the base. So we're given that this whole tube is 1.00 meters, so I'm just gonna write 1 meter. And let's say the acid is on this side. We immerse the acid in that cotton, we soak it in acid, and we're gonna make a salt acid-base reaction. These are gases, but when they make that salt, that's gonna be a solid precipitate that's gonna form. And this occurs a lot in chemistry labs when you have like amines that are fairly volatile liquids. And if you store them anywhere near an acid, you'll start seeing this crusty solid form around the amine lid jar, because some of it leaks out of the jar, and you get this sort of nasty, usually white, or it could be a brown precipitate that forms. But anyway, so it says a white precipitate salt forms 0.267 meters away from the acid. So the salt that forms, here's our salt, it forms right here. And that's at, if we call this, x equals 0 meters, this is x equals 0.276 meters. All right, so this is a little bit different because we know our rate equation here has the rate, I'm going to call R of, we can write a rate expression, right? We can say R acid over R base is going to be equal to square root of M over base, remember inversely proportional here, divided by square root of M acid. So we know that expression from what we went over earlier in this video. That's sort of what is given to us. But what's a little weird is that we don't have rates, right? We have distances. So how are we going to do that? Well, we have to know that distance is speed or rate times time. And so we can write this for the acid and the base. The distance that acid travels is equal to the rate that the acid is going at times the time of the experiment. Now, the time of the experiment is how long it takes to make that salt precipitate. We can write the exact same thing for the base. D base equals the rate of the base traveling times the time that it takes to make the salt. Now, those times are the same. We don't know what that time is, but what we can do is now solve for R acid and R base, because we have that in this equation here. So let's do that. So R acid is going to equal to D acid over time, and similarly R base is going to be equal to D base over time. So now we can go back to this expression where we have R acid divided by R base and plug those in. So R acid again was D acid over time, and we're dividing by R base, so that's going to be like equivalent to multiplying by T over D base, right? We just flip this expression here, and that will then equal the rest of our expression with the square roots. Okay, so at this point we see that the T's cancel. We have the T on top, the T on the bottom, and so then our equation just becomes D acid over D base equals square root of M base over M acid. And so at this point, we just need to plug stuff in and think about this. So D acid is going to be what, 0.267 meters. We have that. And what is D base going to be? Well, D base, the whole tube is 1 meter. And so they met here. So D base traveled 1 meter minus 0.27 meters, which is 0.733 meters. So that's what we're going to put in for how far D base traveled, right? It traveled all this distance here, 0.733. And now we have M base. M base is actually what we are trying to solve, so that we're going to just leave as a variable. But we know, or we can figure out M acid. And so M acid, right, we know what the acid is. It's hydroiodic acid. So we can calculate the formula weight. It's 1.008 grams per mole for hydrogen, looking at the periodic table. And then for iodine, it's 126.904 grams per mole. And so your ending molecular weight is 127.912 grams per mole. And so we'll plug that in for our M acid. That is what our M acid is. And now at this point, it's just a little bit of algebra. So 0.267 divided by 0.733 turns out to be 0.3643. And we have M base, again, is our unknown. And then we have 11.3098 grams square root divided by mole inverse. Okay. Why did those become half square roots there? Because we square rooted them. So technically that's what the units are. Now we multiply 0.3643 times that 11 value. And that gets us 4.12 square root of grams per mole. And now we're going to square the whole expression. So 4.12 squared will get us our final answer. The final answer is about 17 grams per mole. And there aren't that many gases that just exist in chemistry, especially with this low of molecular weight. And so, and we know it's a base. Okay. And so this base is actually what fits is ammonia, right? Nitrogen has a atomic mass of 14, hydrogen about 1. So total that gets us about 17. So we can actually figure out the identity of our base, although strictly speaking, the question was just asking us for our molecular weight. So that's a harder problem of fusion using this tube idea, but no, this is one way you could figure out the identity of an acid or a base, and could work that way.